So the Professor Dr. Dolphy Gilpin has introduced Hafnium, and let's take a look at it from a partial extrapolation of our periodic table here. So I have HF72, that's it here, HF72 atomic number, and 178.86 atomic weight. And above it would be zirconium. It's a behave very similar to zirconium, and below it would be RF. RF would be nil quadium. In the modern form, the RF would be nil quadium. Modern nomenclature. Okay. No. Yeah. 104, we're looking at, that's below the hafnium with atomic number 104. That would be nil quadium. So we look at hafnium here. Atomic number 72. Atomic weight 178.86. That would be, I guess, the most stable isotope. And we do some introductory properties in our notes here. We have hafnium, oxidation state, +4, electronic configuration 4f145d26s2, hafnium shiny, silvery and ductile, that's its appearance, and uses in nuclear reactors, in nuclear power industry, in electronic equipments, in ceramics, light bulbs, and in making of superalloys. And I guess in electronic you also have semiconductors, which is that. Now hafnium is really found freely in nature, and it is presented in zirconium minerals. And as you know, zirconium is one of the elements just above it in group 4 there in the periodic table. And nil quadium would be just below it, which would be RF. It's present in zirconium here at a concentration of 5%, and hafnium is produced by zirconium refining using the NOS process, which is reducing the tetrachloride, I guess the hafnium tetrachloride, with magnesium or with sodium. And there are over like 35 different isotopes of hafnium, with 5 of them which are stable isotopes, and many are lab created isotopes. Now, hafnium is very or relatively expensive because in recent years its demand has risen quite significantly. So, because of the demand of the hafnium, the price has risen, and it's risen due to its use now in the aircraft sector, the gas turbine blades, the aircraft sectors, and the nuclear reactors, more specifically the nuclear submarine. And because of this, there's an increase in the cost price of this hafnium. Now, all isotopes of hafnium are observational, stable, or predicted radioactive. That is, they have not really tested or observed the radioactivity of the hafnium. So they say though that in observational is observed or predicted to be radioactive. So that the actual decay has not been observed for the hafnium. But extrapolatively, it can be considered that some of these stable isotope in the probability will be radioactive. Now, hafnium has a known toxicity. It has no known toxicity. However, usually the compounds of hafnium should be considered toxic. It should be cautioned that they might be toxic, even though the pure metal is non-toxic. It has no known toxicity. However, exposure to, well, the eye and the skin, as usual, most things will give you irritation with the eye or the skin. So even these transition metal, you could definitely expect some form of irritation to the delicate eye and the skin. And the mucous membranes if it's ingested. Once again, the pure metal is considered not toxic. However, compounds of the hafnium should be treated or assumed to be toxic. Better to be safe than to be not sure. Okay. Hafnium production is low compared with the use in nuclear reactors and chemical industries. So that's something that we have observed, that the hafnium production is low compared today with its use in nuclear reactors and chemical industry. And therefore that sort of, as we said before, push up the price because it's in demand. So we have hafnium submarine nuclear reactor. It's using microchips to make the microchip smaller and faster. Smaller and faster performance. And it's used as a neutron absorber. And it's used in the nuclear reactors, control rods, and nuclear submarine. So we have just gone over that again. So I'll just do some emphasis on that. The price of hafnium is between $100 per pound and $100 to $500 per pound, and this depends on the purity and the quality of the hafnium. Well, we could do the calculation from the dollars per gram in this interval of $100 to $500 per pound. depending on purity and quality. That's an easy calculation. We could just go to Google, or if you have any table there or any, make that quick conversion from pounds to gram. The yearly demand of hafnium in the United States is said to exceed 100,000 pounds per year. So we are in the British system here talking about pound, but we could easily convert 100,000 pound per year. And we could convert that to grams. And an emphasis of caution here, we know that most of these lanthanide series elements in the powdered form or in the particle form will explode in air, will ignite in air and form explosive mixture with air. That's a property of most of the lanthanide series metal in the powdered form. And they would form a film, most of them, that prevents further action just in the normal air. But if ignited or heated more, then as this one, if you provoke it, it goes to form the hafnium dioxide, HFO2. So HF plus 2O2 will yield HFO2 solid, which is the hafnium dioxide. And once again, the finely divided hafnium is a hazard, is pyrophoric, making it a fire hazard. And it does not react with water. Now, hafnium plus the halogens, no, will give you the hafnium halides. So you have hafnium solid plus 2F2 gas, give you HF4, which is white. That's a solid. That is a tetrafluoride here. And HF solid, which is a hafnium solid plus 2 chlorine gas, gives you HFCl4, which is white. That's in the liquid form. And HF solid plus 2 bromine gas give you HFBr4, which is the hafnium bromide. And HF solid plus 2 iodine gas will give you the HFI4 solid white. Notice that it's the I4, which is like a tetra chloride or tetrahalide. Most whole mineral acid will not react with hafnium, with the exception now of hafnium fluoride or the hafnium hydrofluoric acid, which dissolve the hafnium, forming fluoro complexes. And hafnium does not appear to react with alkalis. Does not appear to react with the alkalis, which are the bases. But it does react with the hydrofluoric acid. And I guess it will also react with concentrated sulfuric acid as well. Yeah, it will react with concentrated sulfuric acid and hydrofluoric acid. I guess you'll have some sulfate complexes as well, some sulfate complex ions. So that's the introduction to hafnium. As we slowly progress, we wish to cover the whole 118 elements, although not in consecutive order. And then, we don't know what to tell. If we have other calling, if we don't have other callings, then we'll come to do some specialized, like we have specialized uranium and plutonium, and some of the radioactive nuclear elements. Might come to specialize some which has great medical applications.